thanks for the warm introduction. All right, so kind of like he said, so what I want to give you, is it better? No, it's better. So what I kind of try to give you as a takeaway here is that you get more time spending really on the things you like doing. This is developing and not debugging, because I think that's so tedious. And if I have to debug things, it's like you have that curve that you really hate your job and you're so frustrated and it's just so annoying. And then, of course, then you fix the things. It's like you have that level, that high level. And yeah, you love your job and it's all super. And I want to give you kind of a takeaway that you have more of a last level so that you're really happy with what you do and that you get to know some tools, how you can make your life potentially easier with already some agents around there which can help you fix your bugs. And yeah, in the introduction was mentioned, so these are the recent publications. So if you want to go deeper in what I'm covering, yeah, you can feel free, of course, to look it up. All right, so speaking of that, so I'm going over some kind of basics for the landscape in models, then the introduction to the agents, then I will be covering test time compute and tree search because this will help you as well in getting better results. And and I actually see that's a typo because I'm not covering evolutionary code generation. I'm so sorry. This is from a previous presentation. However, we will still start with language model agents. And this is just a very little overview. So what you do is you have your user request, you give that in, and then you have your modules, you have your tools, and also like planning, so you can do reflection, critics, chain of thoughts, all of that to have a better result and give your language model also some tools to help you perform your tasks. And there are different kinds of agents you can use, so like single agents, React, multi-agents, so multi-agents for the more complex architectures, for the more complex tasks, and reflection, and also multimodal, and this is the more interesting part. So if you're having web development or things which have images in it, so you want to go for multimodal, so that has that image understanding. And I was mentioning the more complex, the multi-agents. So these are overviews of common multi-agent architectures. So you have that supervisor architecture. There you have kind of like the team leader of your language models, just different language models. And the supervisor, as the name suggests, he gives it like the model's tasks to fulfill. And they then access their tools, do the task, report back to the supervisor, and then the supervisor decides who gets next to do the task. And if things are way more complex, then you go with the hierarchical architecture, meaning you now have supervisor of supervisors, so you have a team of teams working on your task, and you can diversify the task, and with that, it gets way better, because if you're giving one supervisor or one agent too many things to do, then they won't perform as good. So you need to split it down, make it less complicated for the agents, for the models, and then it performs better. And why is that relevant? Why should you bother with agentic systems? So just to give you a little bit of comparison. So on one side, you see the traditional workflow. So you have the predefined sequences. With an agentic system, it's more dynamic. You have a dynamic decision loop. You have context-aware tooling, tool use, and you can have that human in the loop, so the back and forth with an agent, instruct it, interrupt it, let it know what you rather want to do, tell him it should use another tool. If you have just the traditional workflow, this won't work. You can't interrupt or do anything there. So it's a linear execution. And here we have this, it's iterative and it's self-correcting. All right, so, well, then there are some software engineering agents out there, but do these agents really generalize to visual software domains? So if you're a web developer, can you use that actually? And the answer is no. That's the problem. So with the common tools, the common frameworks out there, this is not really working. So the challenge is really for real-world bugs that go beyond Python. Most of the tools out there you just can't use because they can't comprehend this. So like I said, so most autonomous debugging systems, well, they just don't work. So there is a benchmark which is called SWE bench. And what they do, or what they did, they looked into how different frameworks perform. And they created an own agent-computer interface to make that way easier and way better. Now we'll show you how and why. So you have, for the most things, it's really more focused on Python repositories. It's only text-based descriptions. It's really narrowed down to that. So really the key insight is the current systems is not good. They break if you're going from Python to JavaScript, for instance. So like I said, so we have that benchmark, and this is on the multimodal part. So hence I mentioned, if you're going to use that for software development, use a multimodal agent system, because then it really understands different modalities, which might be important for you for your development. So what they did is they analyzed it on 619 task instances with 17 JavaScript libraries. So they did test a wide variety to get an understanding how good do the systems really perform. And all tasks included images or videos as part of the issues or tests. So issues, they used GitHub issues to let the systems automatically perform and solve those issues in the GitHub repositories. And yeah, different domains were included: syntax highlighting, interactive maps, web UI, and so on. And yeah, like you see, visual bugs matter really. So over 80% of attacks require visual understanding, visual input to resolve actually the issue. So really the key takeaway here again, multimodal reasoning is essential for modern bug fixing agents. And this is an overview how the benchmark diversified the tests, so what they looked at. And also they considered the complexity and difficulty curve. So how difficult are the tasks the agents have to solve? How do they perform? Then they have to solve those things. So for about 40%, it took 1 to 4 hours for a developer. And so this is kind of how they benchmarked how difficult the tasks for the agents are. And it goes from debugging front-end data, visualization bugs, and they really noticed that this is a different beast. It needs more time, more comprehension, more reasoning, and takes way more time and longer than just a normal like backend or whatever Python script development. And this is the setup I mentioned. So this is the agent-computer interface, so ACI. And the cool thing about this is it includes specific ways for the language models to understand. So some of you, or a lot of you probably have been in the panel in the launch room, and they were talking about, yeah, well, but the language models don't understand the problems as well, and they struggle to do that right. And actually, this is where they picked on here. So they said, look, we humans, we use the IDE to help us out with the problems, to solve it, to do it better. So why don't we develop something which specifically language models and agents can use the same way we use IDEs? And this is what they did here. So you have a specific agent-computer interface with language model-friendly commands like navigate repo, search files, edit lines, view files, and so on, to make the life of the LLM easier to help you debugging your code. And yeah, I mentioned it already. So it fixes issues in real GitHub repositories. It performs tasks on the web. You can have it also for cybersecurity vulnerabilities. So there's a special branch which does this specifically. You can do any task you want with it. I share, if you want, I can share the slides with you. Just reach out to me via LinkedIn. So for everyone, just reach out. Yeah, you can really do any task with it. And it's suited for production workflows via GitHub. So it's really production ready. And this was also something mentioned during that panel earlier, that, well, I wouldn't give it to my production code. But with that here, with that setup, you can actually do it. And it can help you speed up the things and really take more time for the things you love to do when you develop your code. And, well, why is it a great fit for software engineering tasks? Like I said, so you have a tailored agent-computer interface. It makes it easier. It's human-like development flow. You have error recovery. You have guardrails. So there was, I don't know if you noticed or if you heard about it, so there was a recent news about the company Cursor. I don't remember the company name, but basically what happened is Cursor then sideways just did something and they couldn't access the code and the things anymore because they got locked out. So here you have guardrails specifically that something like this does not happen. And the interfaces reduce cognitive load to those models. I mentioned this as well. So you have really that specific tooling for them to access to give them a better handle of helping you fixing the bugs. And it's not for the great code development like with Cursor. It's really helping you a lot with bug fixing, so very specific. So yeah, that paradigm I want to cover is like really thinking smarter and not bigger. So there was for a long time the trend that every company went bigger models, more parameters, and yeah, it couldn't be big enough. However, there's that kind of shift now with test time compute, and actually last year in August from DeepMind, there was a paper about this. So they analyzed, well, what will happen if we give the models just more time to think? So the smaller models, give them more time to think. And also, while giving them more time to think, we think about, all right, so how difficult is the task? Let us classify how difficult the task is. And based on this, we are using a specific strategy to iterate over the solution. So basically what you do is you're not using the first output of your model. You give it more time, more iterations, and then based on the strategy, you choose best of n or another method to extract the best result after several iterations. And this is the reason kind of why we did go bigger. So there's that scaling law, so that the more training data you have for your model, the better it generalizes, the better it performs. So this paper was a couple of years ago published by OpenAI, and they kind of, a lot of companies took that up and just developed bigger and bigger models. And not only for language, this applies for literally any foundation models. So time series, image, video, whatever. So yeah, I mentioned this kind of already. So we did go for that large, extremely bigger models, but that doesn't help all the time. So we give the smaller models more time to think, more computing time during inference and test time, and this can really sometimes then outperform, or most oftentimes outperform, the larger ones. And this is kind of how this setup looks. So you have a so-called process reward model, and this helps you evaluate this process. And this is specifically trained on the task, what it should evaluate and perform. And when you give it in the problem for the LLM, you have the intermediate steps, it generates, and then it gets scored, gives the feedback, and then you just iterate, and after the scoring, you get the final answer. And I will show you later on different kind of paradigms which use this also for developing better tests, so that you don't have to write your unit tests yourself. So they actually use that scaling law to increase the diversity and the kind of knowledge of language model, of coding agents and coding models, to give you a better diversity in unit tests and perform overall better. And this is an excerpt from the paper from DeepMind I mentioned. So here are just different paradigms compared. So they found out, like on simpler models, they have that or lower compute budget. It's better to use a strategy like best of n, what I already mentioned, than on harder. It's, for instance, beam search, which performs better. So just kind of a little bit of an insight. And another thing what is really important or interesting right now, and I feel there's also kind of a shift, and I feel like this is the year right now for the intersection and hence the X here between reinforcement learning and large language models. And it's called in-context reinforcement learning. So in context just means that you don't alter the weights of your models. So you have it in context. Also when you do a prompt engineering, so you might give your model examples and then help it guide it to perform better. And this is kind of the same thing what happens here, but with the help of reinforcement learning. And for those of you not familiar with reinforcement learning, there's a very important paradigm, which is the explore-exploit trade-off. So that's the trade-off between gathering new information, so you explore, or the use of that information to then improve the performance. So you exploit what you previously found out. And this is one of my kind of favorite applications or frameworks in that direction, because it's really powerful, and it was actually the first one doing that, exploiting reinforcement learning. So they use Monte Carlo tree search to improve over different iterations, to improve how your language model performs, how your agent performs, and how you can improve it just doing the in-context learning. And yeah, I mentioned already, so it was the first framework. It incorporated reasoning, acting, and planning to really enhance your language model performance. This is a short overview of it. So you have that different stages with selection, the expansion of a tree, the evaluation, simulation, backpropagation, and then the reflection. The reflection is if you fail with the path, with the solution, or solving the task at hand, it stores it, it self-reflects, or you can also give in human feedback, and it stores that feedback. And it uses this for the next time when it's again, starting to solve a problem so that it doesn't make the same mistake the second time. And this is a bit of a breakdown, so how this overall works. So you start from the root, and then you just traverse through the tree and select a node based on a measurement, which is called the upper confidence bound. This is then applied, of course, to the tree. Then you have the expansion. So if a selected node is not terminal, then you expand by generating child nodes. And then you run a simulation from the new node to estimate a value. And then you just backpropagate that values up the tree. And like I mentioned, if that trajectory fails, you store that reflection to improve in the future. And this is another algorithm kind of building on this. They try to optimize it more. And here you see the optimization for math inference scaling across different strategies. And they evaluated, so MCTS is Monte Carlo tree search, and just normal sampling and that rebase. So this is an improvement. However, this is not so efficient, so it takes a lot of computing time, although the results are pretty good. It takes kind of too much computation. And I will show you, I think a slide or two later, another improvement above that rebase. So, but first let us look at the comparison between rebase and Monte Carlo tree search. So high level, so you have also for the Monte Carlo tree search is more high, and although I mentioned here it's slower, it's still higher than some other methods. You don't have that rollouts, which you have with that Monte Carlo tree search. The solution completion is, well, sometimes unfinished. If you're unlucky, it's higher because it looks at, rebase looks at things a little bit different with a candidate solution, so it helps finding better candidate solutions. And because of that, Monte Carlo tree search is a little bit less effective. It's a bit more narrow for the path, and with rebase you have a bit more controlled exploration, and you have a direct reward from the process reward model. So this is really the kind of innovative part they brought in. So what I showed you earlier with the process reward model and say with the test time compute, they leverage that paradigm to improve the Monte Carlo tree search, which was or is not the case with LLMs, what I showed you earlier. And this is another kind of paradigm which also builds upon this. So they actually improve better. So this is very efficient, and it leverages KV cache, and this is key value cache. And basically what this does, it exploits the paradigm for transformers. Then you can, in that cache, in the memory cache, can store the key values and don't have to compute it all the time anew. Just for the next generation, you leverage the previous one, store it in the cache, and generate there the next token. So it's way more efficient. So they leverage this, and with that they get faster results. So they exploit that KV cache in a very efficient way. And this is another example specifically designed to scale the code generation. So if you're looking into probably building upon what I showed you with the SWE agent and want to have maybe plugged in a different model because they actually allow you to do that. So you could do something like using that S here for test time compute scaling for code generation and improve the model you're using in a very simplistic way. So it's really easy to use the code they provided. So the paper comes with code, with a GitHub repository. And then you can improve your model based on the task and the way you things you have. And improve your agent overall for your coding tasks. So if you have something very specific, you could generate a data set and train your model on this. Right, so what is then this? So it's really kind of a hybrid test time scaling for code generation. So it's combining parallel sampling with sequential refinement. So it's kind of an iterative debugging. And it's more robust for code development and coding models. And it's really also grounded in execution feedback, not just the LLM guesses and paths. So the key idea is to use more compute at test time to improve both the coverage and the accuracy of your coding models. And why does this actually matter? So I already mentioned, so yeah, if you want to maybe improve your agent for helping you out fixing your bugs, so why should you matter and even bother with probably using this? So this is why. So for Gwen, it got an improvement of 10%. And if you think about it, 10% is quite a bit. So if your performance gets better, and yeah, and you see here, even if you're going for other models, it nearly matches DeepSeek. So in DeepSeek, well, if you want to deploy it, it's quite costly. So you can actually opt for a smaller model, use that code, use that functionality, and get nearly the same performance. And how does it work? So there are no hallucinated outputs. It relies on real execution. It samples the solutions parallel, so it's very effective. And it iteratively refines. And then it runs the code on those inputs and uses results to select then the best solution. And yeah, this is just another view for the scaling and SW Jim, how to evaluate then those agents. And I see I have question marks wherever. Yeah, this is also for the inference. So the first was for the training time, and this is for the inference time, how this affects and how you can leverage this to actually improve the model performance. And here again, so you see you have that large language models struggle with that accurate first attempt code generation. So you really want to improve that. And with that, you have kind of a way of doing this. So key insights here I want to leave you with is that if you scaling the number, for instance, with that unit test, it improves the quality of the reward signal. So for the reward model, and you get a greater benefit for the challenging code problems. So if you have more difficult tasks, like difficult bugs, like I mentioned, for 1 to 4 hours, if it goes to 4 hours or more, you might want to look into this and in this method to apply to your models. And here is what I mentioned earlier about the scaling of the unit tests for the code reward modeling. So this is another method where they use kind of scaling it dynamically to get better and better unit tests. And also with that, improve how the coding models actually can develop tests for your software. So you don't have to write it anymore yourself. I don't know how you feel. This is something I don't really enjoy. You need to think about a lot of edge cases. And if you have a model and coding model actually performing in pretty well, it's worthwhile looking into it. So yeah, this is kind of the problem. So often fail on first code generation attempts. So you need verifiers, unit tests to re-rank multiple generation solutions. So you can not only use that for your unit tests, but you can use this also in validating the coding models if they actually perform good. So you have a complete system. One writes your unit codes, the other helps you fixing the bugs, then it comes together and it evaluates each other in that whole agentic setup. So basically, the key here is when you scale the number of the unit tests significantly, it improves the quality of these reward signals really for the hard problems to solve. And they used here or developed a lightweight model as kind of a unit test generator trained on synthetic pipeline. And they used also the dynamic scaling. So what I told you about test time compute and the scaling, why it matters, why you should look into it, this was the reason why. So there's a lot of research going on in leveraging this, in generally improving the overall solution that you don't have to deploy that extremely large models. So they used an 8 billion parameter model and improved it with test time compute. All right, so yeah, these are more or less the key takeaways I want to leave you with. So, of course, you have that visual front-end bugs. They require the multimodal reasoning, not just only text-only systems. Then, like I mentioned very much at the beginning, look into that agent-computer interface because it gives you, or gives the agent actually kind of an IDE to solve your bugs, your problems. And then if you want to improve your models, look into test time compute. It can boost the reasoning. It makes things smarter, and you don't have to deploy and look into those extremely large models. And then I oftentimes get asked, well, with all that agents, am I sometimes then redundant as a software engineer? So this is why I want to have that kind of no. It's not that it gets obsolete. It should be seen more that you can get more free time for the things you actually love doing, like developing good software, good code, and leave the tedious and repetitive and not so interesting things to the agents, give them to solve and have more fun. Yeah, more fun time for yourself.